And eigenthings, that is eigenvalues, vectors, eigenspaces, eigenbases, these are all going to be the focus of our last 6 lectures. We also only have 6 lectures left, including today. Okay, so this is what we're focusing on for the remainder of the semester. And I gave a little bit of motivation for what all of this stuff is useful for last Thursday. But to recap, eigenvalues and eigenvectors, we're going to use them for 2 things. One, by understanding them and how they work, it'll give us a deeper understanding of things we've already seen. So for example, understanding what eigenvalues and eigenvectors are will tell us, for example, now this is coming from a question in homework 9, why the matrix X transpose X plus lambda I, why is this always invertible? For some context, this was a problem in homework 9 where you had to take the gradient of some other empirical risk function that kind of looked like mean squared error, but it had some extra stuff added on. And you ended up finding that the optimal W vector involved the inverse of this matrix. And I kind of just said in the homework, this matrix is always invertible, which is like a pretty big claim because this matrix isn't always invertible, right? The invertibility of X transpose X depends on whether or not X's columns are all linearly independent. But the claim is that whether or not that's true, this thing is invertible, okay? Why is that? Well, the answer has something to do with eigenvalues and eigenvectors. And then another thing that we can revisit once we know about eigen stuff is the convexity of vector to scalar functions. And we can use eigen stuff to develop a second derivative test for convexity that works when you don't have just a derivative, but you have lots of partial derivatives, okay? But in addition to that, that is, in addition to helping us better understand stuff we've already seen, eigenvalues and eigenvectors will allow us to understand a new class of problems, okay? And one type of problem, and by the way, there's a whole new chapter, chapter 5.1, that we'll start with today, and there will be a 5.2 for Tuesday. The motivating example that I like to use when introducing eigenvalues and eigenvectors, and I alluded to this on Thursday, and we will get to some of that today, is you can use it to derive Google's original algorithm for ranking websites on the internet. So you can actually read the research paper written by the 2 co-founders of Google, one of whom went to Michigan for undergrad, by the way, but they both wrote this as PhD students at Stanford. You can click this to read the actual paper they wrote in the year I was born, 1998, and you can see that it says PageRank blah, 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 blah corresponds to the principal eigenvector. Okay, so like the algorithm Google originally used to rank pages on the internet when you would search for something involved the type of math we're going to walk through today. Okay, and we're going to look at a simpler example of how the PageRank algorithm works. That's what they call their algorithm today, and then you'll look at this example in more depth in homework 10. Okay, so this is like a new class of problems we can look at when we know about eigen things. Okay, but first, let's start with the core or the basics, which we introduced back last Thursday. Pretend I have a square that is an n by n matrix A. What is an eigenvalue or eigenvector of A? And note that everything we're about to do today involves square matrices. So rectangular matrices we'll think more about next week. For now, we're going to focus on square matrices. What is an eigenvector of A? Anyone know? Yeah, Tiger.
It's like some vector where if you multiply that with A, it'll lead to a scalar multiple if it's...
Good. I don't know why this disconnected. Yeah, that's exactly right. We know that you can think of multiplying a vector by a square matrix as a linear transformation within the same vector space, right? If your initial vector has 3 things in it and you multiply it by a 3 by 3 matrix, the new vector is also going to have 3 things in it. And there are some English language descriptions we gave for the type of transformation that could lead to. Like it could be a stretching if you're using a diagonal matrix. Or the example that we saw a lot is that it could be a rotation if it's an orthogonal matrix. Or maybe it's just none of those and it's just some arbitrary transformation that we would still call a linear transformation, right? So we're working with square matrices, which means you should think in terms of linear transformations from Rn to Rn. But indeed, as we just heard, an eigenvector V is a vector such that when you multiply it by A, what comes out is a new vector whose direction is unchanged. That is, it still lives on the same line that it originally did. It may point in the exact opposite direction, or it may be longer or shorter, but the key is that its direction is unchanged. Okay? And any vector that satisfies that property is called an eigenvector of A. So the English language definition of an eigenvector is that when multiplied by A, V's direction didn't change. It was just scaled by a factor of lambda, which is the corresponding eigenvalue. Okay? So eigenvalues and eigenvectors come in pairs. With an eigenvector, there is a corresponding eigenvalue. Do we agree? So if, I don't know, 3, 4 is an eigenvector of a matrix, it's an eigenvector of that matrix corresponding to a specific lambda. Okay, and so what we care about are these pairs or combinations of eigenvalues and eigenvectors. Okay? One of the first examples we looked at last class, and one that we will look at quite a bit today, just because the numbers are nice, is 1, 2, 2, 1. Can anyone think of what the eigenvalues and eigenvectors of 1, 2, 2, 1 might be? Can you think of an eigenvector? Thinking of the eigenvalues is more challenging. It's easier to think of what are the eigenvectors. That is, what vectors, when you multiply it by A, will still point in the same direction that they originally did, just maybe with a different length. Any guesses? Yeah.
1, 1.
Yeah. The intuitive answer is 1, 1. Why is that? Well, we'll say let V equal 1, 1. Well, then AV, what does it end up being? Well, you take the dot product of 1, 1 with the rows here, and you get 1 plus 2, which is 3, and 2 plus 1, which is 3. AV is just 3, 3, which is 3 times 1, 1. Which means V has this nice property that when you multiply it by A, what comes out is a vector in the same direction as V, just with a scalar multiple up front. What this tells us is that V is an eigenvector of A with eigenvalue 3. Now the thing is, this is not the only eigenvector with an eigenvalue of 3. Can you tell me another one? Like, sure, it's true that if you multiply A by 1, 1, you get 3 times the original vector. Can you give me another vector that satisfies that property? If I multiply it by A, I get 3 times the original vector. Any guesses? Yeah.
1, -1.
Yeah, I could also try -1, -1. What does that give me? Well, it gives me -3, -3, which is still 3 times whatever I started with. So, -1, -1 is also an eigenvector, or eigenvec, of A with lambda equals 3. Same lambda. And hopefully it's not too much of a stretch to say that if I just multiply this eigenvector, 1, 1, by any number that's not 0, what I get back out when multiplying that new eigenvector by A is just 3 times whatever I started with. That's the key. Any vector that points in this direction to begin with, after you pass it through A, is just going to be triple what it originally was. Okay, so 1, 1, you should think of as defining a direction for this eigenvector. And so I'll say if V is an eigenvector, so is CV for any non-zero C. The reason I'm saying non-zero is because we define, eigenvectors can't be the zero vector. Because any matrix times the zero vector is just going to be the zero vector once again. Okay? And so we'll say the eigenvectors need to be non-zero. So as we will see, eigenvalues could be zero. That's a perfectly fine thing. Eigenvectors, though, can't be. Okay, does anyone know what the other eigenvector direction of A is? Right, so we have one eigenvalue or eigenvector direction. It's any vector in the line spanned by 1, 1. Is there another? Yeah.
Is it -1 and 1?
Yeah, what if we try -1 and 1? Well then, just to show you intuitively here, or just to show you quickly here, if I had -1 and 1 here, what would I get back? Okay, I can write this out. What would this give me? Well, on the top I'd have -1 plus 2, and on the bottom I'd have -2 plus 1, which gives me 1 minus 1, which is telling me that what is an eigenvalue of the matrix? What is the corresponding eigenvalue? -1. Yeah, it's a little tricky because it looks like the same thing just shuffled around, but this is indeed just -1 times what I started with. So V, and why don't I call this V1 and lambda 1, and here I can call these V2 with -1, 1 is an eigenvector corresponding to lambda 2 equals -1. Yeah.
Is there any trick or easy way to come up with these eigenvectors?
Good question. So how did we find -1, 1? Are we supposed to always just do it by guessing? The answer is no. The answer is no, we don't have to always do it by guessing. There is a systematic way we're going to look at how to find eigenvalues and eigenvectors. I wanted to start with a relatively small example so that we don't focus too much on the computation. But in maybe 5 minutes, I'll show you what is the formula for finding eigenvalues and eigenvectors. Good. First, though, I want to visualize what we can deduce by these two eigenvectors of A. So to recap, A has two eigenvectors, 1, 1 and -1, 1. But really anything that's a scalar multiple of either of them is also an eigenvector. Here's a question. If I take a linear combination of V1 and V2, is that also an eigenvector? So if I take something times V1 plus something times V2, is that also now an eigenvector? Why is your guess no?
If we just take one of each and add them together, it would be 0, 2, which is just not
Is not an eigenvector. Right, exactly. If the statement I was implying were true, that is, if it were true that you can take any linear combination of this and get an eigenvector, it would mean that anything is an eigenvector of A. Because these two vectors, 1, 1 and -1, 1, sorry for all the swiping, they span all of R2 because they don't already point in the same direction. And in fact, if you have two eigenvectors corresponding to different eigenvalues, they can't point in the same direction because each eigenvector defines its own direction, okay? But if it were true that a linear combination of eigenvectors is a new eigenvector, well then it would have to mean that anything is an eigenvector of A, but I can think of lots of vectors that aren't eigenvectors of A, so that statement's not true. But what do these eigenvector directions look like? Let's take a look. This is the one for A. Good. So this is similar to a graph I drew in class on Thursday, but now there are some more examples in the notes. In orange, I've drawn the direction of the first eigenvector, V1, which is 1, 1. And coincidentally, I did them in the same order as I did in the notes. But here, V1, like we saw before, is 1, 1. The sort of grayed out version of V1 is what I get back when I multiply V1 by A. And what we are seeing is that when we start with an eigenvector and multiply it by A, what you get back is a new vector that lives on the same line. Okay? The same thing is true for V2. Remember V2 on the last slide I wrote it as negative 1, 1. Here I've intentionally wrote it as negative 2, 2 to emphasize that it doesn't have to be the eigenvector you happen to find itself. Any scalar multiple of it is also good. So here, if I start with 2 times V2, where V2 is the thing I found on the last slide, when I pass it through A, that is when I multiply it by A, what I get back out is negative 1, which is the eigenvalue, times whatever I started with. Okay? And so the key thing to focus on here are the eigenvectors, are these coefficients. The eigenvalues are these coefficients, eigenvalues. Are we clear on what I mean by that? Like I started with double the eigenvector, and what I get back is negative 1 times double that same eigenvector. If this was 5v1, this would be negative 1 times 5. Sorry. If this were 5v2, this would still be negative 1 times 5v2. Do we agree with that? Okay. And so in these like dotted lines, we see these dotted lines, like there's some up here, some down here. These are like defining the lines or directions that are eigenvector directions. What this means is if I pick off any vector that lives on this line or lives on this line, it's an eigenvector of A, which means you multiply A by that vector, it's still going to live on that same line. Okay, here as we saw, its direction could technically be flipped, but it still lives on that same line. Okay? X down here, which is just some other random vector, 0, negative 1, or sorry, negative 1, 0, is not an eigenvector. Why is that? Graphically, I can see that because when I multiply x by a, it lives on some other line now. It's not on the same line that it originally was. Whereas in the eigenvector cases, multiplying by a keeps you on the same line. That's the easy way to think about it. Eigenvector, you multiply by a, you live on the same line. Do we agree with that? Okay. In addition to everything I just said, you might notice something about the specific v1 and v2 we ended up with. You like squint at this x, what do you notice? Well, you don't have to squint, but what do you notice? Yeah. They happen to be orthogonal, yeah. The eigenvectors of this A happen to be orthogonal. Let me just say here, v2 from the last slide was negative 1, 1. Do we agree with that? Right? These two lines intersect at a 90-degree angle. Now, is it true in general that if you take two different eigenvalues and compute their eigenvectors that they have to be orthogonal? The answer is no. This matrix A just happens to have a special property that guarantees that its eigenvectors are orthogonal. And we actually really like that property. If you had to guess about this A, what do you think its property is? Yeah?
Symmetric?
Yeah, it's symmetric. Okay? Symmetric matrices have orthogonal eigenvectors. That's an important fact that we're not going to get to prove today, but that'll be the focus of what we start talking about next week. But keep it in mind for now, because I'm pretty sure it'll come up in homework 10. Symmetric matrices have orthogonal eigenvectors. Good. But just to show you that this is not always the case, let me draw a similar picture for some other matrix. Here's some matrix B, whose eigenvalues and eigenvectors aren't as simple as the previous example. You can tell that its eigenvectors aren't orthogonal, though. Right? Its eigenvectors are v1 here, and v2 is going to be 1/3 of whatever this is. Again, just to illustrate, I drew something that's not exactly a v2, but it's some multiple of it. And you see that all that happens is it gets stretched by whatever the eigenvalue is. So here the eigenvalue is negative 1.45, and the other one is 3.45. Okay? But the eigenvectors aren't orthogonal. And I'm just showing you that this is a possible case when you have a 2x2 matrix. And in general, if you don't know anything else about a matrix, there's no reason to believe that its eigenvectors for different eigenvalues are orthogonal. Okay? So here, you just highlight what the eigenvalues are. One eigenvalue is 3.45. The other is negative 1.45. Okay. And here, x, -1, 0, is still not an eigenvector. I mean, we can think of a matrix it's an eigenvector for, but it's not an eigenvector for this b or this a, because when multiplying by either of those, ax isn't in the same line as x was. Okay? So right now we're focusing on graphically what does it mean for a vector to be an eigenvector. What questions do we have with that general premise? Comfortable so far, loosely with an eigenvalue and eigenvector? Good. You may wonder, where did I find lambda 1 and lambda 2 here? Right? What formula did I use? Answer is, I didn't use a formula. I used Python. And so, this is in the notes, and again, you'll practice with this a little bit in homework 10, but there's a useful function, np.linealg.eig, which gives you the eigenvalues and eigenvectors of the matrix. Now, the key thing to note, and so firstly, here are the eigenvalues. They're the same ones you saw on the last slide, 3.45-ish and -1.45-ish. Okay, here's a trivia question for something that's going to come up later in lecture. What do you notice about the eigenvalues? Just think abstractly here. Like, imagine this was, I don't know, some just math test, and someone said, what do you notice about these numbers? 100.
The numbers after the decimal are the same?
Yeah, the numbers after the decimal are the same. What does that imply? Like, what operation could you do between them to get a nice result? Yeah.
You could subtract them.
You could subtract, well, if you subtract them, then, yeah, you'd add them because this one's negative. What you notice is if you add them, the decimals go away, and what do you get? 2. Okay, a fact we're going to see later on is that the sum of the eigenvalues is always equal to the sum of the diagonal. Not just for a 2 by 2. It's true for any matrix, 3 by 3, 4 by 4, and so on and so forth. And there's a term for the sum of the diagonal of a matrix. It's called the trace of a matrix. So the trace of a matrix is equal to the sum of its diagonals. I was going to bring this up later, but now is as good a time as any. Observe. Lambda 1 plus lambda 2 equals 2, which is sum of the diagonal.
So the sum of the eigenvalues is equal to the
Sum of the diagonals, yeah. There's another fact that's also true. This one might blow your mind even more, but it's less obviously true with these numbers. What do you think is true about the product of the eigenvalues? Again, you can't really tell what this would be because these numbers are nasty, but if you had to guess, similar kind of vibe. Sum of the eigenvalues is always something nice. It's equal to the sum of the diagonal. What do you think the product of the eigenvalues is? Yeah.
Is it something like the determinant?
Yeah, it's the determinant of the matrix. So if you were to multiply this number and this number, you get exactly -10. Sorry, -5. So that's also true. Product of eigenvalues equals product of determinant. Now in general, you can imagine if we have an n by n matrix with n eigenvalues, just knowing those 2 facts is not enough to figure out what the eigenvalues are, right? Because if you have n unknowns being your n eigenvalues, you need n equations about them. But this is a nice check to see if you calculated the right eigenvalues and eigenvectors. You know that their product has to always be the determinant. Okay. The other thing I wanted to mention is that when you use np.linealg.eig, the columns of the array it gives you back are the eigenvectors, not the rows. Though sometimes it'll print it misleadingly and you'll think it's the rows. So this is the first eigenvector, and this is the second. So the columns are the eigenvectors. But remember, an eigenvector is not uniquely defined. Like if 1, 1 is an eigenvector, then so is 2, 2. So that means whoever implemented np.linealg.eig had to make a design decision. Well, there's infinitely many scalar multiples I could return. Which one do I return? And which one does it look like they chose to return? Yeah. The unit vector, good. Right? If I think about the example, these eigenvectors are not particularly nice looking. But if an eigenvector of my matrix was 1, 1, what it would say here is 1 over square root of 2 and 1 over square root of 2. So I wouldn't say that. I would say 0.707 and 0.707. Because that's the unit vector in that direction, right? Graphically, what this is saying is, well, for this eigenvalue of 3.45, I could return any of these things. I could return this, 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 this. And so to keep things uniform, I'm going to always consistently return the unit vector one. Good. But these two eigenvectors are not orthogonal, and in general they're not. They just happen to be in the first example because that matrix was symmetric, and that's something we'll dive deeper into in just a bit. Yeah.
So is the product like the determinant because it's sort of like scaling along the eigenvectors by the eigenvalues?
Good. That's good intuition, right? The fact that the product of the the product of the eigenvalues is the determinant has something to do with how we can interpret the eigenvalues as stretching some vectors. And we're going to dive deeper into that over the next few lectures. What I want to address now is actually, okay, there's two examples I want you to work on before we get to the next big point. So I'm going to give you some time to work on this. Consider the matrix A, which is 1, 4, 3, 12. What do you notice about A? Yeah.
It's the determinant of 0.
Yeah, the rank of A is 0. It has two eigenvalues. One of them is 13. What is the second? And what are the eigenvectors? Don't answer yet. I want you to discuss this. Or do you have a question about the material, or do you have an answer to this?
Yeah, is the rank 0?
Sorry. I'm bad at math today. Rank 1. Good. That's the first thing I want you to ponder. The second thing is, before we saw A equals 1, 2, 2, 1, had lambda 1 equals 3 with v1 equals 1, 1, and lambda 2 equals negative 1 with v2 equals negative 1, 1. What are the eigenvalues of A squared? What eigenvectors? Okay, two problems. I'll give you some time to think about both of them. And the first one, you may already have a guess, because I introduced the product is determinant thing earlier than I intended on. And so the answer to lambda 2, okay, someone tell me, well, what is the answer? What is the second eigenvalue? 0, right? Because we know they have to multiply to the determinant, which is 0. But what is the corresponding eigenvector? I want you to think about that and how that relates to things that were on the midterm. And then in this case, play around with it a little. What are the eigenvalues and eigenvectors of A squared? So I'll give you a few minutes. I'll walk around, and then we'll take these up. So first, what is the other eigenvalue? We said this already, but what is it? 0. How do we know? Well, we can use the trick I mentioned earlier, which is that the eigenvalues have to sum to whatever the diagonal sums to, which is 13, and they also have to multiply to whatever the determinant is, which is 0. What other number with 13 adds to 13? 0, and also multiplies to 0. Good. How do we find the eigenvectors? Well, first let's find v1. This one isn't as much a conceptual question as it is a computational question. How do I find the eigenvector satisfying, or the eigenvector for the eigenvalue 13? Any ideas? How do I find v1? And ideally, we're doing this by not guessing and checking. How do we do it? Guesses? Yeah.
It's set up like a system of equations.
Yeah.
So it's like v1 plus 4v2 equals 13.
Yeah, all we're looking for are scalars v1 and v2. You know what, I'm not going to use v1 and v2 because those refer to vectors here. I don't know, let's call them x and y, sure. Such that what you get back out is 13x and 13y. We agree with that? And what you'll notice when solving this system is that both equations tell you the same thing. Why is that? Why are there infinitely many solutions to this equation system? And just to illustrate that, the first gives me x plus 4y equals 13x. And the second gives me 3x plus 12y equals 13y. Right? This, if you rearrange, tells you 4y equals 12x, which tells you y equals 3x. Did I do that right? Yeah, I think so. And then here, this also tells me 3x equals y. They both say the same thing. Did something go wrong, or is this what we'd expect it to say?
This is expected because the rows are dependent.
The rows are dependent, but this would actually happen even if we were using a invertible matrix. Why?
It's because it can be any vector on that line.
Exactly. There should be infinitely many solutions for x and y, because this would be a solution, and so would this, and so would this, and so would this. So there shouldn't just be one answer. There should be infinitely many. And in the 2x2 case, what that tells you is if there are two equations, one of them is useless. Right? Both. Since any vector on that line works. So I don't know, the easy solution to me is just plug in x equals 1. So y equals 3. So lambda 1 equals the vector 1, 3. That works. Okay? You just can't plug in 0, because then you get 0, 0, and 0 is not supposed to be an eigenvector. But this tells us, as you've seen, eigenvalue and eigenvector both start with a v, and it's easy to say the wrong thing. But this is an eigenvector, of course. That's good. Okay, what about the eigenvector v2? How might I find it? And what is this related to in terms of things we've seen studying for midterm 2? What is this? Yeah.
It would just be anything in the null space of A.
Good. Why is that?
Because 0 times the vector is going to equal a 0 vector, so you need A times that to equal the 0 vector, which is only possible if it is a 0 vector or in the null space.
Exactly. So what we're seeing now is a nice connection between whether or not a matrix is invertible and whether or not 0 is an eigenvalue. 0 is an eigenvalue if and only if the matrix isn't invertible. Because if it is invertible, then it doesn't have a null space. Well, it does, but it only has a 0 vector, and we're not considering that. That is, if it's invertible, AV equals 0 is only satisfied by the 0 vector, nothing else, which means 0 can't be an eigenvalue. But if it's not invertible, well, then there are lots of vectors v that give you this. And all of those would be eigenvectors for the eigenvalue of 0. So here, can you read off to me an eigenvector here?
4 and -1.
Yeah, 4, -1, right? And remember, the easy way of figuring out vectors in the null space are you just reverse engineer what combination of the columns gives you the 0 vector. Right? And 4 times the first is equal to the second. So 4 times the first minus the second will give you the 0 vector. Good. And so this is a basis for the null space of A. Good.
So if your null space was like 2-dimensional, is it still going to be like 1?
Good question. So imagine we're dealing with a 3x3 or a 4x4 matrix whose null space is 2-dimensional. Then you're right. The eigenvectors wouldn't lie on a line, but they'd lie on an eigenspace that is 2-dimensional. And that's not just unique for the null space. Like, as we will soon see, eigenvalues can have multiplicities. Like, you can think of a matrix who has the same eigenvalue twice. And what that could mean, it doesn't always mean this, but it could mean that there are multiple directions that correspond to eigenvalues or eigenvectors for that eigenvalue. We're going to see all of that in more detail on Tuesday. But good, you're thinking about the right thing, which is that the set of eigenvectors for a particular eigenvalue can be more than one-dimensional. But we're starting with the easy case where they're both one-dimensional. Good. So are we clear on the connection between an eigenvalue of 0 existing and the matrix being invertible? 0 is an eigenvalue if and only if the matrix isn't invertible. If it is, 0 can't be an eigenvalue. And if 0 is an eigenvalue, then it's not invertible. We're good on that? Good. It's important enough to just have written down here. A has an eigenvalue of 0 that's equivalent to A is not invertible. Good. What about this other example, where I start with A from before, and we knew its eigenvalues and vectors. What are the eigenvalues of A squared? What are the eigenvectors of A squared? Any guesses? Well, one way to approach this is to just calculate what A squared is. Right? It'd be 1, 2, 2, 1 multiplied by 1, 2, 2, 1. What does this give me? In the top left, it's going to give me 1 plus 1. 1 times 1 plus 4, 2 times 2, which is 5. Bottom left, it's going to give me 2 plus 2, which is 4. Top right, 2 plus 2, which is 4. Bottom right, 4 plus 1, which is 5. We agree with that? And in the case of A, we deduced that 3 was an eigenvalue for the eigenvector 1, 1 by just noticing that both rows sum to 3. Here, what do both rows sum to? 9. So we hypothesize that 9 is an eigenvalue for the same eigenvector, 1, 1. Similarly, if you take negative 1, 1, multiply it through, what do you get? Negative 1, 1, what does it give you? Yeah, it's also an eigenvector still, but now the eigenvalue isn't negative 1, what is it? 1. So the conclusion here is that if V is an eigenvector of A with eigenvalue lambda, it's also an eigenvector of A squared with eigenvalue lambda squared. And so a big application area for eigenvalues and eigenvectors is taking repeated powers of a matrix. Like a thing we're going to do by the end of today's lecture is say, what is this matrix to the power of 10 or 100? And you can answer that without having to actually multiply 100 matrices. Instead, you can do some quick calculations using the eigenvalues raised to the power of 100. Okay, so eigenvalues and eigenvectors tell you what's really going on with a matrix. And just as a quick proof here of the fact that if V is an eigenvec with eigenval lambda of A, then what does that tell us? Let's try and figure out what A squared V would give us. Okay? Just experimenting. Let's assume that the thing I just told you is not true. How would we deduce that? Well, ideally this would equal to something times V. How could I start by decomposing this? Like how could I work towards figuring out what this would be? Yeah.
It'd be like A times AV.
Yeah, I can write this as AAV. Right, similar vibes to the sorts of proofs we did when we looked at invertibility of matrices, right? But what is AAV? Yeah, that's lambda V there. But this is lambda is just a scalar, so I can bring that out. So I have lambda AV again. And boom, again, I can use the lambda V part. So I have lambda squared V. Then V is an eigenvec of A squared with eigenval lambda squared. Okay, and you can imagine how this argument would extend to the power of 3, power of 4, so on and so forth. To like fully do that, you'd have to use proof by induction, but like I think you're convinced that if we did this again, you could show it for power of 3 and then power of 4. Okay, one thing I'll say is that the converse of this statement is not necessarily true. It's true in the matrix that we've seen so far, but I could make a matrix where A squared has an eigenvector that A doesn't have. Can anyone think of an example? It's possible for a squared to have an eigenvector that A doesn't have. And so I'll emphasize that this is only one direction. Yeah.
In the previous slide, like, why can't you say like, it has the same eigenvalue, but you know that A is like some new vector?
It's because I'm starting with the premise that AV equals lambda V. That's the only thing that we've used here. And then my question is, well, what happens if I do A squared times V? Knowing that AV equals lambda V, what can I do with that? Is all I've done. So I'm assuming that this V is an eigenvector of A. And my question is, just starting with AV equals lambda V, what does that get? What I'm emphasizing here is that just because an eigenvector is an eigenvector of A squared doesn't automatically make it an eigenvector of A. Okay, this example is maybe a little in the weeds and we don't need to emphasize it for today, but I want you to think in terms of rotations. So one thing that we discussed last class, and there's a bit more about in the notes, is that in general, a rotation matrix doesn't have real valued eigenvectors. Right? Imagine your matrix rotates by 30 degrees. Like, what vector is still going to point in the same direction after being rotated by 30 degrees? Nothing, right? But in using the technique we're about to see, it still does have two eigenvalues and two eigenvectors. They're just complex number based. Like, they're not real eigenvalues and real eigenvectors. I mean, they're real as in they exist. Like, they're not monsters or ghosts or something. They're like not real value, not real numbers, okay? Though there are two edge cases of rotations that do have eigenvalues and eigenvectors. What if you rotate 180 degrees, for example? That's just reflecting the vector, right? And if you start here and rotate 180 degrees, you point here, that's still on the same line. So you could find an eigenvalue, eigenvector there. And then if you rotate by 360 degrees or by 2 pi, well, then you end up in the same place. So there are some edge cases where rotations could have eigenvalues, eigenvectors, but in general, for some random degree, they wouldn't. So some random theta, they wouldn't. And so the example I've thought of is if we think of multiplying by A as applying an operation, multiplying by A squared is applying the operation twice, right? So imagine rotating by 90 degrees, for example. Right? No vector is going to point in the same direction after rotating 90 degrees. But if you apply that twice, which means you rotate 180 degrees, well then some vectors would, all vectors would point in the same direction. So that would be a case where A squared has lots of eigenvectors, but A doesn't have any, at least in terms of real numbers. Okay? Just thought experiment. So I'll say think in terms of rotations.